We're going to look at Newtonian mechanics, except now we're going to talk about components and angles. And why do you need components and angles? I'm glad you asked. Because sometimes your force isn't exactly along x or y. All right, it's at some angle, theta. So we need to break it into components, which are the parts that point in the x direction, which we'll call fx, and the part that points in the y direction, which we'll call fy. Then you're going to need to figure out, well, what's the value of fx and fy? How much of f points in the x direction? How much points in the y direction? And for that, we're going to use our good friend trigonometry. So your x component in this case is on the adjacent side, so it becomes f cosine theta, and your y component becomes f sine theta. Always consult your triangles when you're trying to figure out whether or not to use sines and cosines. And then what we're going to do is we're going to take this and use it to express our vector in component notation, which says I move this far in the x direction, and then I move this far in the y direction. All right? And the reason is because if I go this way and then this way, I end up at the exact same spot as if I just went along f at some angle theta. And this becomes very, very useful because x and y, the directions, they're not intertwined. What this does for us is that if I know I have a net force in some direction, it causes acceleration in that some direction, whatever that direction happens to be, I can split up and I can worry about just the forces in the y direction and just the forces in the x direction, which makes the problems easier to solve. For an example of this, let's look at this stoplight. How do we start? Well, we always draw some type of diagram. We draw a force diagram. Here it is. And then we establish our axes. So I'm going to make this the x hat, and I'm going to make straight up the y hat. Now, as we mentioned, we need to break this into components. So I've got T1. This will be T1x, and this would be T1y. So I can tell that T1y, if I want this part, is just T1 times sine of 37 degrees, because that's the angle. T2 is going to be T2 sine 53 degrees, which would be right here. This would be T2y, and this up here would be T1y. And the weight of the system pointing straight down, remember negative means down, is just 100 newtons. For the x direction, well, I want the adjacent side, so same type of thing using cosine, and there is no part of weight pushing down. Well, I have two equations and two unknowns. How fortuitous of us. So let's start looking at the x equation. Why not? Because there were only two pieces. Note, always work vertical, and the reason why is because one side of the equation is max and one side is f net. It is very easy to forget to write the other half if you work horizontal, but you need both sides. You need the ma side, and then you need the sum of forces side. So please work vertically. Makes it easier to see where you're going. After that little brief announcement, we're going to go back, and then we're going to solve, and I get T2 is equal to 1.33 T1. Well, that covers one equation. Let's look at y and figure out the rest. So if I look at this, I've got T1 sine 37 plus T2 sine 53 degrees equals negative minus 122 newtons equals 0. But let's go substitution. I know that T2 is equal to this from my y equation, which now I can just algebra it out and get that T1 is equal to 73 newtons. Combine that with my previous expression, where T2 equals 1.33 T1, and I get T2 is equal to 98 newtons. So we used two equations, two unknowns, but you need to use the knowledge of x's and the y's in order to get your final answer. Go ahead and work through the example kind of slowly, and then ask if you have questions in class. As a little side note, theta 2 is actually 53 degrees. That's a typo right here, so this should be 53. The math I did works out with 53 degrees, so I apologize for that. But just keep in mind, it is 53, so I'm sorry if that caused confusion. And we're going to go back to this block on a ramp, except now we're going to add friction. So first thing, let's draw our force diagram. I've got gravity pulling down. Notice that if I just used this as my standard axis, x hat, and then here, y hat, I'd have to break things. Maybe there's a better way to do this. Oh, and plus, the block is actually going to accelerate that way. So I'll have components of acceleration. I wish there was a solution. Like turning your head sideways, which works. So all you have to do is you rotate your axis. Typically, I like to put the axis where the acceleration is, or at least one of them, and the other at 90 degrees. Because what happens, oh look, now friction is just in the x direction. Your normal force is just in the y, and the only one you have to break up is the force of gravity. So let's go ahead and do that. This angle, by the way, is theta, the angle of your initial ramp. You can kind of see that if I put this here. If this is theta, then we drop that straight down. How far did I have to turn my head to make this? Like this was our old up. Old up. I have to turn my head theta degrees in order to do that, which means this angle right here is theta as well. I'm happy to explain that in more detail. So again, keep your acceleration on one axis. Now we're going to play this out just like we did before. We're going to consider the y-axis first, because guess what? It's acceleration in the y-axis. 0. It's not going into or out of the ramp. Always work vertical, and I get normal force minus the y component of gravity, mg cosine theta in this case, is equal to 0. So I get n equals mg cosine theta. Great for the y's. Now let's use x's. ma and the x, well, it's going to roll down the ramp, so that's not going to be 0. But I can say that I have the component of gravity. This is Fg in the x direction. And then in the other side, pulling away, this is my force of friction, minus mu, and this was n, minus mu n. All right. So we divide by m. Again, those m's will all cancel out. I get our acceleration is equal to g sine theta plus negative. I'm going to group a few terms, I think, and we'll just get our acceleration is equal to this wonderful expression. Well, I hope that was helpful, and we will talk later in class. Ask if you have questions, and I will see you then.